Hello and welcome to our night observatory. Please make yourselves comfortable. Tonight we are going on a journey that will make you question the stability and permanence of even the largest structures in the universe. Have you ever looked up at the night sky and truly tried to grasp the sheer scale of what you are witnessing? Billions of stars, each one a sun, and billions of galaxies, each one an island containing hundreds of billions of those very suns. Now imagine that one of these galaxies, one of the largest, brightest ones, simply vanished. It didn't explode, it didn't fade, it disappeared, leaving behind only a gaping void and utterly bewildered astronomers. This isn't a hypothesis. This is a real-world mystery known as the Abell 2261 cluster problem. Tonight we will attempt to understand how such a thing is even possible and why the best minds in humanity are still struggling to find an answer. Prepare yourself. Our lecture for sleep is about to begin. To truly appreciate the depth of this mystery, we first need to understand exactly what we are dealing with. Imagine not just a city of stars, but an entire metropolis built from hundreds, even thousands, of those star cities. That is a galaxy cluster. These are the most massive, gravitationally bound structures in the universe. They act like gigantic cosmic spiderwebs, where the knots are dense pockets of galaxies, gas, dust, and, of course, vast quantities of dark matter. The specific cluster we are focusing on is catalogued as Abell 2261. It lies approximately 2.7 billion light-years from Earth. At its heart, just like in any other similar cluster, there should be the single brightest and most massive galaxy, what astronomers call the brightest cluster galaxy, or BCG. This is the queen, the gravitational monarch, who has gradually consumed dozens of her smaller neighbors over cosmic timescales. It is this queen, this central galaxy in the Abell 2261 cluster, that is the source of all the confusion. It is fundamentally wrong. Its core, its heart, is missing. Where there should be a tight, dense knot of billions of ancient stars and a monstrous, supermassive black hole, astronomers observe only a blurred, diffuse cloud. It's like finding a throne room with neither the throne nor the king. This is where one of the most intriguing investigations in modern astrophysics began. So, let's dive into the specifics of the initial observation, the one that kicked off this whole mystery. It all started with a routine deep dive into the data beamed back by the Hubble Space Telescope. Astronomers who use this legendary instrument are well accustomed to spectacular views of deep space, but what they spotted right at the center of the Abell 2261 galaxy cluster was truly unprecedented. Located within this colossal cluster was a galaxy known simply as ACG 2261395. It was immense, bloated even, with its light scattered across an area spanning more than 2 million light-years in diameter. That's 20 times wider than our own Milky Way. But its luminosity wasn't distributed naturally. Typically, these giant elliptical galaxies, which formed from countless mergers, feature an extremely bright, compact core. That's the spot where star density reaches its maximum, the gravitational hub, where most of the mass is concentrated. But here, that core was gone. Instead, the center of the galaxy appeared empty and puffed up, as if someone had physically scooped out its heart. Scientists' initial reaction was a mixture of disbelief and technical skepticism. Could it be an artifact of the data processing? Maybe some quirk specific to the Hubble instruments? They ran dozens of checks. The data was reanalyzed repeatedly using every possible method and filter. But the outcome remained consistent. The central region of the galaxy was abnormally dim and sparse. It was like looking at a photograph of a major city at night and finding that its downtown business district, where thousands of skyscraper lights should be blazing, was completely blacked out. This observation became the starting point, the first act in a cosmic drama that is still unfolding today. The scientists realized they hadn't found an error. They had found a fundamental anomaly that urgently required explanation. What could possibly inflate the core of one of the most massive galaxies in the universe, effectively erasing its center? To fully grasp the shock astronomers experienced, we first need a deeper understanding of what a brightest cluster galaxy, or BCG, truly is. This isn't just the largest galaxy in a cluster, it's a true cosmic monster, a cannibal that grows by devouring its neighbors. In the dense environment at the center of a galaxy cluster, collisions and mergers are routine. Over billions of years, gravity drags smaller galaxies towards the core, where they are captured and consumed by the central giant. Each merger adds stars, gas, and, crucially, combines their central supermassive black holes. This process, known as galactic cannibalism, culminates in the formation of a colossal elliptical galaxy, defined by an extremely massive and dense core. Theoretical models and observations across hundreds of other clusters confirm this picture. BCGs invariably possess an exceptionally bright and distinct center. It is their calling card, the direct result of their violent history. The galaxy at the center of Abell 2261 completely defies this rule. Its bloated and dim core suggests that something truly extraordinary has occurred. This is not just an anomaly, it's a direct contradiction of established models of galaxy formation. Imagine an archaeologist discovering an ancient city, only to find an enormous empty crater where the temple or ruler's palace should be. This immediately raises fundamental questions about the location's history. Similarly, the missing core in the central galaxy of Abell 2261 is forcing astrophysicists to completely rethink their assumptions about the life and death of galaxies in the universe's most extreme environments. This is an anomaly that could either point toward a new, previously unknown physical process or force us to admit that our current theories are incomplete. Lurking deep in the heart of every major galaxy, like a beast sleeping in a dragon's lair, is a supermassive black hole. This isn't just a metaphor, it's an established astronomical fact. Our own Milky Way galaxy orbits the object known as Sagittarius A star, which holds the mass of over 4 million suns. Andromeda's black hole is even more massive, but in the brightest cluster galaxies we are discussing, the central black holes can reach staggering figures, up to tens of billions of times the mass of our Sun. These objects aren't just passive gravitational centers, they play a pivotal role in galactic evolution, regulating star formation and sculpting the overall structure of the galaxy. Finding a giant galaxy without a supermassive black hole at its core is like finding a living organism without DNA. It's simply impossible within the scope of our current understanding. And this is where the mystery of Abell 2261 becomes even deeper. If the central galaxy lacks a core, then where is its supermassive black hole? It has to be there. It should be one of the most massive in the observable universe, perhaps reaching 100 billion times the mass of the Sun. Its gravitational influence should have gathered a dense cluster of stars around it, precisely the core that we don't see. The absence of the core directly suggests the possible absence of the black hole itself in its usual spot. This thought was so radical that most scientists didn't even dare voice it at first. Where could a black hole, the size of our entire solar system and weighing billions of suns, have possibly gone? It can't just evaporate. It can't simply explode. It is one of the most stable and long-lived objects in the cosmos. Consequently, the investigation shifted from asking, "Why is the core so puffy?" to the far more unsettling question, "Where is the black hole?" The hunt for this missing monster became the primary objective for everyone studying this enigmatic cluster. When you encounter the impossible, you are forced to consider the most extreme hypotheses, and the first theory that emerged from the minds of astrophysicists felt straight out of a Hollywood blockbuster. What if the black hole was ejected from its galaxy? While it sounds like pure science fiction, this idea has a very real physical foundation, linked to one of the universe's most exotic phenomena, gravitational waves. According to Einstein's general theory of relativity, when two massive objects like black holes orbit each other and finally merge, they create ripples in the very fabric of space-time. These gravitational waves carry away a tremendous amount of energy and momentum. If the merger is asymmetric, for example, if the black holes have different masses or are spinning in different directions, then the gravitational wave emission will also be asymmetric. This is similar to a rocket moving forward by expelling a jet of gas backward. In the case of black holes, they emit a jet of gravitational waves in one direction, and then, due to the law of conservation of momentum, they receive a powerful, recoiling kick in the opposite direction. This effect is known as gravitational recoil, or simply a kick. Calculations show that the speed of this kick can be colossal, hundreds or even thousands of kilometers per second. This velocity is more than enough to overcome the gravitational pull of even the most massive galaxy, sending the newly born, merged black hole into an eternal journey across intergalactic space. This scenario fit the observed data perfectly. Imagine, within the center of the Abell 2261 cluster, two giant galaxies merged. Their supermassive black holes rushed toward each other, engaged in a deadly dance, and finally coalesced into one. At the moment of coalescence, an asymmetric burst of gravitational waves occurred, and the newborn monster, massing tens of billions of suns, was shot out of the center of its home galaxy like a cannonball. As it fled, it dragged some nearby stars along, while the remaining stars in the core, suddenly stripped of their gravitational anchor, scattered, forming the exact bloated and diffuse halo that we observe. This theory was elegant, beautiful, and terrifying. It explained everything. But like any truly great scientific theory, it demanded proof. The concept of an ejected black hole was thrilling. But for it to become more than just an elegant hypothesis, astronomers needed to locate the crime scene, or perhaps more accurately, the smoking gun, the runaway black hole itself. How do you find it? Black holes, by definition, don't emit light. However, they aren't totally invisible. As a black hole moves through the intergalactic medium, its immense gravity pulls in surrounding gas and dust. This infalling material spirals into an accretion disk, heating up to millions of degrees and beginning to glow brightly, especially in the X-ray spectrum. Therefore, a wandering supermassive black hole should appear as a bright pinpoint source of X-ray emission located far outside the center of its former host galaxy. Furthermore, even after being ejected, such a black hole still retains colossal gravity. It might drag along a small entourage of its nearest stars, forming what's known as a hypercompact stellar cluster. This cluster would be extremely small yet incredibly bright and dense, detectable by the Hubble Space Telescope. Finally, as the black hole flies through the gas within its former galaxy, its gravity should compress that gas, triggering bursts of star formation. This would look like a chain or an arc of young blue stars tracing the runaway's trajectory. Armed with these predictions, astronomers launched a full-scale hunt. They meticulously combed through Hubble images, searching for tiny, bright stellar clusters or suspicious chains of young star nurseries. They aimed one of humanity's most powerful X-ray telescopes, the Chandra X-ray Observatory, at Abell 2261. Their goal was simple: to find the bright pinpoint that would give away the missing monster's location. This was akin to finding a needle in a haystack millions of light-years wide, but the stakes were simply too high. What was on the line was the confirmation of one of the boldest ideas in modern astrophysics. The Chandra X-ray Observatory provides us with a unique window into the universe, allowing us to see the hottest and most energetic processes in the cosmos. Launched by NASA in 1999, Chandra offers unmatched clarity in the X-ray spectrum. While the Hubble Space Telescope sees stars and galaxies in visible light, Chandra reveals accretion disks around black holes, supernova remnants, and gas heated to millions of degrees filling massive galaxy clusters. It was Chandra that held the primary hope in the search for a supermassive black hole believed to have been ejected from the Abell 2261 cluster. Scientists requested and received significant observation time on the telescope, pointing its sensitive detectors directly at the center of this puzzling cluster. They expected to see a bright X-ray source, the telltale signature of accreting gas spiraling onto a rogue black hole. The observations spanned many hours, painstakingly collecting every precious photon arriving from deep space. Following this, the long and meticulous data analysis began. Computers sifted through gigabytes of information, constructing detailed maps of the X-ray emissions and subtracting background noise. Scientists held their breath, examining the resulting images. They were looking for that single point, that definitive signal that would confirm their theory. But nothing. To their profound disappointment, no bright, compact X-ray sources that could be confidently linked to a wandering supermassive black hole were detected. They did find several faint clumps of X-ray emission, but these could have been anything, from background galaxies to small pockets of hot gas. None of them possessed the necessary brightness to match a supermassive black hole actively consuming matter. This was a major blow to the gravitational recoil theory. Of course, one could hypothesize that the black hole was simply not accreting gas for some reason. Perhaps it was moving through a region of very low-density intergalactic medium, but this seemed highly improbable. The Abell 2261 cluster is teeming with hot gas, and a wandering object of that size simply could not fail to leave a noticeable trace. The lack of an X-ray signal didn't completely disprove the theory, but it made it far less likely. The mystery was not only unresolved, but had become even more puzzling. If the black hole wasn't ejected, then where is it? The failure of the Chandra observations forced scientists to return to the drawing board and consider alternative scenarios. Perhaps they were looking in the wrong location or for the wrong object entirely. This led to a second major hypothesis, less dramatic perhaps, but certainly no less intriguing. What if the black hole never left? What if it's still right there in the galactic center, yet invisible to us because there are almost no surrounding stars left? This concept is known as the galactic stripping or shelling out hypothesis. It suggests that the central galaxy in Abell 2261 is the result of not just one, but a series of major galactic mergers. Let's visualize the scenario. Two massive galaxies, each hosting its own supermassive black hole, collide and merge. The black holes begin to draw closer, but this process is far from instantaneous. Instead, they orbit one another, forming a binary black hole system. This binary system acts like a gigantic gravitational blender. Its chaotic rotation disturbs the orbits of stars in the combined galaxy's core, progressively ejecting them onto much wider, more elongated orbits. This action effectively scours the stars away from the core, making it significantly less dense and visually diffuse. Now imagine that soon after, a third galaxy merges into the system. Its black hole also rushes toward the center, forming a highly unstable triple system. The dynamics of such a triple system are even more chaotic and destructive to the stellar core. Over billions of years, through a cascade of such mergers, the central region could be almost entirely cleared of stars. The result is precisely what we observe, an enormous distended galaxy featuring an extremely dim and sparse core. Hidden deep within its center, invisible to our instruments, are not one, but possibly two or even three supermassive black holes that have yet to fully merge, their ongoing gravitational dance having effectively expelled every nearby star. This hypothesis elegantly explained the missing bright stellar core without resorting to the exotic idea of a runaway black hole. It posits that the black hole, or holes, remains exactly where it should be, simply surrounded by a vacuum of its own making. The core stripping hypothesis seemed plausible, but it had its own set of drawbacks. Firstly, achieving the level of core clearance observed in Abell 2261 would require highly specific merger conditions. Instead of a single powerful impact, we would need a series of consecutive, dry mergers, meaning collisions between galaxies that are already low on gas. If too much gas were present, it would cool and form new stars in the center, recreating a bright core, which clearly didn't happen. Statistically, finding a cluster with such a uniquely specific merger history is highly improbable. Secondly, even if stars were ejected from the center, they couldn't simply vanish. They should have formed a massive extended stellar halo surrounding the galaxy. While a halo is indeed observed, its structure and density don't perfectly match model predictions. It seems the stars aren't just missing from the center. The galaxy appears to have fewer stars overall than its mass would suggest. However, the main argument against this theory revolved around the black holes themselves. If the center truly holds a binary or triple system of supermassive black holes, they must eventually merge. As we know, the merger process is accompanied by the powerful emission of gravitational waves. Even if the gravitational wave kick wasn't strong enough to eject the resulting black hole, the merger itself should have left traces, specific distortions in the galaxy's structure, which astronomers have yet to find. Furthermore, if the black holes haven't merged yet, they should be interacting with the surrounding gas and stars, creating specific radio and X-ray signatures, which are also conspicuously absent. Thus, the core stripping hypothesis also failed to provide a complete and satisfactory answer. It explained the bloated core but raised new questions about why we don't observe any of its other predicted side effects. The scientific community found itself at an impasse. Both leading theories, the ejection theory and the core stripping theory, had strengths and weaknesses. Neither could fully account for all the eccentricities of Abell 2261. It became clear that a breakthrough would require a new tool, a fresh perspective on the problem. And now, taking center stage, is a new player, the James Webb Space Telescope, the greatest hope of modern astronomy. Launched in late 2021, JWST is the successor to Hubble, yet it boasts fundamentally new capabilities. Its main advantages are its massive 6.5-meter primary mirror and its unique ability to view the universe in the infrared spectrum. But why is this infrared capability so crucial for solving the mystery of Abell 2261? First, infrared light penetrates cosmic dust far better. If the rogue black hole, or its stellar entourage, is obscured by dust clouds, Webb will be able to spot them where Hubble saw only darkness. Second, Webb specializes in observing the old, cool stars that make up the bulk of giant elliptical galaxies. It can create a far more accurate map of the stellar mass distribution in the central galaxy than Hubble, definitively confirming or refuting the presence and size of the void at its core. But perhaps the most critical factor is Webb's unprecedented sensitivity. It is capable of detecting even the faintest and most distant objects. If a hyper-compact stellar cluster, the entourage, dragged away by the ejected black hole, is hiding somewhere near the central galaxy, Webb is the absolute best instrument for the job. It will be able to distinguish such a cluster from ordinary globular clusters or background galaxies based on its color, size, and stellar composition. Astronomers studying the Abell 2261 puzzle are pinning huge hopes on JWST. Observations of this mysterious cluster are already planned and may even be underway right now as we speak. The data Webb collects could provide decisive evidence supporting one of the current theories, or, even more intriguingly, it might deliver a completely new surprise that forces us to invent a third, even crazier hypothesis. We are living in a unique time where the answer to one of the cosmos's greatest mysteries could be delivered within the next few months or years. Whatever the ultimate explanation may be, the very existence of an anomaly like Abell 2261 already carries profound implications for our cosmic understanding. This isn't just a local peculiarity, it's a direct challenge to the fundamental models of galaxy evolution. If the theory of gravitational recoil holds true, it would provide the first direct observational evidence that supermassive black holes can actually be hurled out of their host galaxies. This means invisible, dark monsters, each weighing billions of solar masses, could be roaming intergalactic space. This would open up an entirely new area of study, the population of rogue, supermassive black holes. How frequently does this occur? What kind of influence do they exert on their surroundings? Could they potentially capture gas and seed the formation of new dwarf galaxies? This fundamentally changes our view of the universe's demographics. Conversely, should the stripping hypothesis be confirmed, it would highlight just how complex and chaotic the dynamics are at the hearts of galaxy clusters. This would necessitate a complete overhaul of current galaxy and black hole merger models, requiring the inclusion of new, more subtle effects. This could imply that the supermassive black hole merger process takes significantly longer than previously modeled, and that the existence of binary and even triple systems of these objects is not an exception, but rather the norm within cluster cores. But there remains a tantalizing third possibility. What if both of these theories are incorrect? What if we are witnessing the manifestation of entirely new, unknown physics? Perhaps it relates to the strange properties of dark matter, which constitutes the majority of the cluster's mass. Or maybe it's connected to the inherent nature of black holes themselves, to the physics occurring beyond the event horizon. The mystery of Abell 2261 is a textbook example of how science truly works. It identifies an anomaly, something that refuses to fit the existing paradigm, and this becomes the crucial growth point for new knowledge. This cosmic puzzle forces us to step beyond conventional frameworks and ask the boldest questions about the structure of our universe. Let's return to the prime suspect, gravitational recoil. To truly grasp the magnitude of this phenomenon, we need to consider the sheer energy released during the process. The merger of two supermassive black holes is, simply put, the most powerful event in the universe since the Big Bang itself. In a fraction of a second, the energy radiated away in the form of gravitational waves exceeds the light energy output of every single star in the observable universe combined. That is an astonishing, mind-boggling figure. If even a minuscule fraction of that energy is directed asymmetrically, it is enough to propel the resulting black hole to truly colossal speeds. The underlying physics is highly complex, requiring the most powerful computer simulations to solve Einstein's field equations. These simulations demonstrate that the magnitude of the kick depends critically on two main parameters: the mass ratio of the merging black holes and the orientation of their spins, their axes of rotation. The maximum recoil is achieved when the black hole's spins are oriented in opposite directions and lie within the plane of their orbit. In this ideal scenario, the recoil velocity can reach 5,000 kilometers per second. That's nearly 2% the speed of light. For a giant galaxy like this, even the escape velocity is only a few hundred kilometers per second. Theoretically, then, ejecting a black hole is more than just plausible, it's entirely possible. But how probable is such an ideal scenario? Statistically, most mergers should involve a more chaotic spin orientation, leading to much smaller recoil velocities. To explain the anomaly in Abell 2261, a massive kick is required, which in turn demands a very specific merger configuration. This makes the ejection hypothesis possible, but somewhat far-fetched from a probability standpoint. Scientists are essentially saying, yes, it could have happened, but for that to occur, the black holes would have had to align in a very precise, highly improbable way. That is precisely why the lack of direct evidence, such as a detectable wandering X-ray source, so heavily undermines this theory. It demands an exceptional event without providing exceptional proof. But what if we're searching in the wrong place? What if the ejected black hole is invisible in X-ray light simply because it's starving? Let's imagine this black hole truly received a powerful gravitational kick and is now hurtling through intergalactic space. If it doesn't encounter dense enough gas clouds along its path, accretion will be extremely weak. There wouldn't be enough material falling into it to create a bright accretion disk visible to the Chandra Observatory. In that scenario, the black hole would be virtually undetectable, but is there another way it might betray its presence? Yes, through the phenomenon of gravitational lensing. According to the general theory of relativity, any massive object warps the fabric of space-time around it. Light from distant sources passing close to such a massive body will be bent, as if passing through a gigantic lens. A supermassive black hole, even a wandering one, acts as an extremely powerful gravitational lens. If it happens to pass exactly along our line of sight to a distant background galaxy, it will dramatically distort that galaxy's image, creating characteristic arcs, rings, or even multiple images. This phenomenon, when caused by a single, compact object, is often referred to as microlensing. Searching for such events is an incredibly difficult task. It requires constantly monitoring millions of background stars and galaxies, hoping to catch a fleeting, characteristic distortion. In the case of Abell 2261, this would necessitate repeated, deep field observations using instruments like Hubble or Webb to try and capture that ephemeral signal. This is vastly more complicated than simply locating a stationary X-ray source. However, it remains one of the few viable ways left to detect a truly starving rogue black hole. So far, observations with the required precision and duration haven't been completed, but this challenge may become a primary objective for future space missions. The idea that an invisible lens, weighing billions of solar masses, is lurking somewhere in the cosmic darkness is simultaneously terrifying and fascinating. Let's take another look at the Hubble Space Telescope and what it revealed, beyond the mystery of the missing core. Hubble's deep-field images of this cluster are truly a work of art. We can see not only the massive central galaxy, but also hundreds of smaller galaxies scattered across the entire field of view. And among them, there's something very interesting going on. The images show numerous distorted galaxies stretched into thin, elongated arcs. These aren't some strange, exotic galaxy types. And this is a textbook example of strong gravitational lensing. The entire galaxy cluster, Abell 2261, thanks to its immense mass, most of which is dark matter, acts like a massive natural lens. It bends the light from even more distant galaxies located far behind it, allowing us to see them magnified and highly distorted. By studying these arcs, astronomers can precisely map the mass distribution within the cluster. They can create a detailed gravitational map showing exactly where the mass is concentrated. And this map delivers another surprise. It confirms that the cluster's center of mass aligns perfectly with the position of that central, massive galaxy. This is a critical point. It means the gravitational center hasn't shifted at all. This poses a serious problem for the ejection theory. If the supermassive black hole, which constituted a significant fraction of the core's mass, was violently ejected, it should have caused a slight but noticeable recoil in the center of mass of the entire galaxy relative to the cluster's overall mass center. The galaxy would have effectively slingshot or kicked back in the opposite direction. But the gravitational lensing data doesn't show this. The centers align with extremely high precision. This is strong evidence suggesting that whatever event took place, it happened right at the cluster's gravitational center, and the bulk of the mass remained exactly where it was. This tips the scales towards the hypothesis of stellar stripping or some other form of internal dynamic rather than an external ejection event. Every new detail we gain from observations seems to only add more layers to what is already an incredibly tangled puzzle. Besides optical light and X-rays, astronomers have another window into the universe: radio waves. Radio telescope observations can shed light on processes involving magnetic fields and high-energy particles. Active supermassive black holes, in particular, are often powerful sources of radio emission. They eject giant plasma streams, the so-called jets, from their polar regions, which stretch for hundreds of thousands of light-years and glow brightly in the radio spectrum. Were radio observations conducted for Abell 2261? Yes, of course. Using instruments like the Very Large Array in New Mexico, scientists thoroughly scanned the cluster. They were searching for radio emission originating either from the central black hole, or a binary system, or from some kind of wandering radio source. And once again, the results were disappointing. No powerful radio source was detected at the galactic center, the kind you would expect from such a massive black hole. This doesn't mean it isn't there, it just means it is currently dormant or inactive. It's not actively consuming material or emitting jets. This is actually quite normal for many giant elliptical galaxies. Crucially, however, they also failed to find any sign of a wandering radio source, one that would be expected if a rogue black hole was dragging magnetic fields behind it. The absence of a radio signal, combined with the lack of an X-ray signature, makes the hypothesis of a wandering black hole even more tenuous. It seems that if this cosmic monster does exist, it has decided to be maximally discrete, failing to reveal its presence in any part of the electromagnetic spectrum. This leaves us with two options. Either the black hole is so quiet that our current methods can't detect it, or it simply isn't there, meaning we need to search for a completely different explanation. This state of uncertainty is both frustrating and invigorating, pushing scientists toward newer, more ingenious search methods. Let's look at the shell stripping hypothesis from a slightly different angle. We've discussed how a binary supermassive black hole could function as a cosmic gravitational beta, scattering stars outwards. This process is often termed the slingshot effect. When a star passes close to the binary black hole system, it receives a powerful gravitational acceleration, hurling it out of the galaxy at immense speeds. Such stars are known as hypervelocity stars. Detecting a population of these stars flying away from the center of Abell 2261 would serve as strong circumstantial evidence that a binary black hole is indeed lurking at the core. But how can we find these stars? It's incredibly difficult. The galaxy is extremely distant, and we cannot resolve individual stars within it, save for the rare sight of a supernova explosion. However, we can analyze the integrated collective light from the stellar population. Using spectroscopy, we can measure the average velocity and, critically, the spread of stellar velocities, known as velocity dispersion, across different parts of the galaxy. If a gravitational slingshot is truly active in the center, we should see an abnormally high velocity dispersion in the central region, a so-called heated core. The stars there should be moving much more chaotically than in typical galaxies. Such measurements have been performed using large, ground-based telescopes equipped with powerful spectrographs, and the results turned out to be ambiguous. Yes, there is an observed excess of high-velocity stars, which may well indicate dynamic core heating. However, the effect is not as dramatic as some binary black hole models predict. Perhaps we are only seeing the residual effects of a process that was more active in the past. Or perhaps the process itself isn't operating exactly as we modeled it. This is yet another piece of the puzzle that doesn't fit neatly into any single scenario. It doesn't disprove the shell-stripping hypothesis, but it doesn't offer definitive confirmation either. It only emphasizes how complex and multifaceted the physics governing the hearts of galaxies truly is. We are only seeing the echoes of titanic processes that took place billions of years ago, and we are trying to reconstruct the entire play based on those faint echoes. While we await the highly anticipated data from the James Webb Space Telescope, theorists aren't sitting idle. They continue to build increasingly complex and detailed computer simulations, attempting to reproduce the unusual structure observed in the galaxy cluster Abell 2261. These simulations are our only way to effectively play through billions of years of galactic evolution within just weeks or months of supercomputer time. In these virtual universes, scientists model the collision of galaxies with varying masses, different gas content, and black holes spinning in multiple directions. They tweak dozens of parameters, searching for the unique combination that results in the formation of an overinflated galaxy lacking a bright central core. Some of the latest simulations are yielding particularly intriguing results. It appears that creating this structure doesn't necessarily require a powerful kick that completely ejects the central black hole. Instead, a moderate recoil kick suffices. This kick doesn't throw the black hole out of the galaxy entirely, but places it into a highly eccentric, oscillating orbit. The black hole essentially behaves like a massive pendulum, swinging back and forth through the galactic center. Each passage through the core acts like a powerful shockwave, scattering stars and dynamically fluffing up the nucleus. Over time, this mechanism could lead to the formation of the exact diffuse structure we observe. In this scenario, the black hole remains within the galaxy, but is not situated in the center. Rather, it is somewhere along the periphery of its vast orbit. This explains why we don't observe it at the nucleus and why it might currently be X-ray invisible if it resides in a region of low gas density. This pendulum scenario presents an attractive compromise between the two leading hypotheses. It requires neither the complete ejection of the black hole nor the existence of a complex system involving multiple, unmerged black holes. However, it too must be observationally tested. JWST could potentially detect this displaced black hole if it is still surrounded by even a small amount of accreting gas or stars. The simulations are ongoing, and each new model provides observational astronomers with fresh insights into exactly what and where they should be looking. Let's take a slight detour from the mainstream theories and consider something far more exotic. What if we're not dealing with standard black holes at all, but with something else entirely? In recent years, an idea has gained traction in theoretical physics, the concept of so-called boson stars. These are hypothetical objects composed not of ordinary matter, fermions, but of bosons, such as axions, which are strong candidates for dark matter particles. Boson stars can be just as compact and massive as black holes, yet they lack both an event horizon and a singularity. They are, essentially, incredibly dense clumps of a bosonic field. Interestingly, models suggest that when two boson stars merge, they might behave completely differently from black holes. Instead of simply uniting, they could potentially explode or scatter, ejecting much of their mass in the form of scalar fields. Could it be that what we are observing in the center of Abell 2261 is the aftermath of two supermassive boson stars merging rather than black holes? Such an event could completely destroy the central object, leaving behind only an inflated stellar halo. This hypothesis admittedly sits right on the bleeding edge of modern science. We currently have no direct proof that boson stars even exist. Nevertheless, it's a perfect example of how mysteries like Abell 2061 encourage scientists to think outside the box. When standard explanations fail, you have to look into the boldest and most untested corners of theoretical physics. If the James Webb Space Telescope fails to locate the missing black hole, these exotic ideas will become increasingly relevant. Perhaps this cosmic anomaly isn't just a flaw in our galaxy evolution models, but the first indication of entirely new physics operating beyond the standard model. Let's talk about the timescales involved. We are observing the Abell 2261 cluster as it was 2.7 billion years ago. That's how long the light took to reach us. This means the catastrophic event that caused the core to vanish must have happened even earlier, perhaps 3 or 4 billion years ago. This is a critical point. In the immense time that has passed since then, the system would have evolved dramatically. If the black hole was ejected, it would have already traveled millions of light years away from its host galaxy. Finding it now is like trying to track a specific bullet fired from a rifle in the 19th century. It could literally be anywhere. Alternatively, if a binary black hole gravitational slingshot was at work, those billions of years should have allowed the system to settle down. The binary orbit would have decayed due to gravitational wave emission, and the two black holes should have eventually merged. Perhaps we are observing the galaxy during a very specific, fleeting stage of its life, right after the core was disrupted, but before the system settled into a new equilibrium. This idea of a cosmic instant makes our observation even more unique. It's as if we accidentally glanced through a window at exactly the right second and caught the immediate aftermath of a cosmic drama. This might explain why we don't see systems like this everywhere. Perhaps this is an incredibly rare and short-lived phase in the history of galaxy clusters. On the other hand, this compounds the difficulty of the task. We are trying to reconstruct events from the deep past using very limited and aged clues. It's similar to paleontology, except instead of dinosaur bones, we have the light distribution from a distant galaxy. Every photon arriving from that region carries information about those ancient events, and the job of scientists is to decipher this message from the past. This entire story wouldn't be possible without decades of technological advancement. Let's start by giving credit to the incredible instruments that allowed us to even pose this kind of question. It all began with ground-based telescopes. In the mid-20th century, they enabled the astronomer George Abell to compile his famous catalogue of distant galaxy clusters. Next, the era of space telescopes arrived. The Hubble Space Telescope, launched in 1990, delivered unprecedented image clarity, free from the distortions of Earth's atmosphere. It was Hubble that first allowed us to properly examine the anomalous structure of that central galaxy. The Chandra X-ray Observatory opened our window into the world of high energies, enabling us to search for hot gas plunging into black holes. Meanwhile, ground-based giants like the Keck Observatory telescopes in Hawaii or the Very Large Telescope in Chile, with their massive mirrors and complex spectrographs, allowed us to precisely measure the speeds of stars within this distant system. And now we have the James Webb Space Telescope, a modern marvel of engineering that promises to look even further and see even more detail. Each of these instruments represents the culmination of work by thousands of engineers, scientists, and programmers. Every single image or spectrum we receive is the direct result of complex operations and many, many years of effort. The story of Abell 2261 is not just about a cosmic enigma. It's also a powerful story about human curiosity and ingenuity, fueled by our relentless desire to understand the universe, regardless of the cost. And as long as we have the capability to build such astonishing instruments, we will continue to uncover new mysteries and, sooner or later, find the answers. This technological race for knowledge truly stands as one of the most inspiring sides of modern science. Let's move on to another crucial aspect, the role of dark matter. We know that galaxy clusters are composed primarily not of stars and gas, but of this enigmatic substance that neither emits nor absorbs light, yet reveals its presence purely through gravity. The dark matter halo surrounding Abell 2261 is hundreds of times more massive than all its visible galaxies combined. It is this halo that holds the entire system together. So, what role might dark matter have played in this particular cosmic mystery? Firstly, it creates the overall gravitational potential within which the galaxies move. Its distribution fundamentally defines the trajectories of any mergers. Secondly, during a cluster merger, while the stellar components of the galaxies interact strongly and scatter, the dark matter halos pass straight through each other with almost no resistance. However, they still exert a gravitational drag on the normal matter. This effect, known as dynamical friction, causes more massive objects, such as supermassive black holes or galactic cores, to slow down and spiral toward the center of the common gravitational potential. In the ejected black hole scenario, the black hole would not only have to overcome the pull of its own galaxy's stars, but also the colossal gravitational influence of the entire dark matter halo. This means the required kick velocity would have to be even higher than previously estimated. Conversely, in the shell-stripping scenario, the dynamics of a binary black hole situated deep within a dense dark matter halo can become extremely complex. Some theories suggest that dark matter might form a highly dense peak or cusp at the very center, which could significantly influence how stars are stripped away. Since we still don't know exactly what dark matter is or how it interacts with itself, its precise role in this puzzle remains one of the great unknowns. Solving the mystery of Abell 2261 may ultimately give us crucial, indirect insight into the very nature of this elusive substance. Perhaps the most intriguing aspect of this whole mystery is the realization that we may not be the first civilization to ever ponder this. If intelligent life exists somewhere else in the cosmos, any civilization reaching a sufficient technological level within the Abell 2261 cluster would have witnessed this anomaly directly, or rather, through their advanced telescopes. Consider a civilization residing on a planet in one of the cluster's adjacent galaxies. To them, the central galaxy wouldn't be a faint smudge like it is for us. It would be a massive, dominant fixture in their night sky. They would have monitored it throughout their entire history. They would have watched it devour neighboring galaxies. And then they would have borne witness as its brilliant core suddenly vanished. What profound impact would such an event have had on their science, philosophy, or religion? The sheer realization that structures as immense as a galactic core can simply vanish would likely constitute a fundamental shock to their civilization. Perhaps right now, 2.7 billion light-years away, other scientists, completely alien to our understanding, are aiming their instruments at this very enigma, developing their own theories, and eagerly awaiting data from their advanced observatories. This is, admittedly, pure speculation, but it drives home the point that the laws of physics are universal. And if the laws are universal, the great mysteries the cosmos presents us with may also be universal. We all, humans and hypothetical extraterrestrials alike, are explorers of the very same boundless cosmos, and objects like Abell 2261 serve as a shared challenge for any intelligence, no matter where in space it happens to arise. Beyond tracking down the black hole itself, scientists are also searching for other indirect clues that might shed light on this system's history. One such piece of evidence comes in the form of globular clusters. These are dense, spherical groupings of hundreds of thousands or even millions of very old stars that orbit galaxies like cosmic satellites. Large galaxies, such as the central galaxy in Abell 2261, should host thousands of these clusters. Studying their distribution and motion can reveal a great deal about the galaxy's merger history. If the central galaxy formed by consuming numerous smaller galaxies, it would have effectively stolen their globular clusters as well. This means its overall system of globular clusters should be vast and highly extended. The Hubble Space Telescope did indeed find an immense number of these clusters surrounding the galaxy. Analysis of these clusters showed that they are distributed quite symmetrically and lack any obvious signs of the violent recent disturbance one might expect from a supermassive black hole ejection. Instead, their movement is consistent with a slow, gradual dynamical heating of the system caused by numerous past mergers. This provides another small but crucial piece of evidence supporting the stripped envelope hypothesis. However, there are nuances here. We are currently only seeing the brightest clusters, and the full picture might be more complicated. The James Webb Space Telescope, with its ability to detect fainter and more distant clusters, will be able to map this system in much greater detail. This may finally allow us to choose definitively between the two competing scenarios. Every detail, even one as small as the distribution of tiny star clusters, is critical in solving this cosmic detective story. But what if we're overlooking the obvious? What if there was no disappearance at all? Some skeptics put forward the radical idea that this galaxy was simply born this way. Perhaps there are rare formation conditions under which a giant elliptical galaxy can form without a dense central core. For instance, imagine it wasn't formed through hierarchical mergers, but rather from a smoother, larger-scale collapse of a massive gas cloud, one that somehow failed to form a central, supermassive black hole. However, this primordial defect hypothesis faces serious challenges. Firstly, it contradicts virtually every modern model of cosmological structure, which are founded on the idea of hierarchical clustering. Secondly, it is difficult to imagine a mechanism that could prevent the formation of a supermassive black hole in such a massive object. Gravity is relentless. At the center of such a deep gravitational well, matter should inevitably condense and collapse. Thirdly, we observe numerous signs of mergers within this system, such as an enormous stellar halo and a large population of globular clusters. This is clearly not a quiet galaxy that grew peacefully in isolation. Despite its unlikelihood, this idea cannot be completely dismissed. The universe is constantly surprising us. If all other hypotheses are eventually disproven, scientists may have to return to this most radical of ideas, that what we are seeing is not the aftermath of a catastrophe, but simply a completely new, previously unknown type of galaxy. That would arguably be the most thrilling outcome of this entire investigation. This whole story might sound incredibly abstract, totally disconnected from our everyday lives. Why should we even care about events that took place almost 3 billion years ago in some distant corner of the universe? But the truth is, this mystery is directly relevant to our own existence. We live in the Milky Way, which is itself part of a small cluster of galaxies called the Local Group, and our own galaxy is currently on a collision course with our closest major neighbor, the Andromeda Galaxy. In about 4.5 billion years, they will begin to merge, forming a new, gigantic elliptical galaxy, which some astronomers jokingly refer to as Milkomeda. Their central, supermassive black holes, Sagittarius A star, and its far more massive counterpart in Andromeda, will eventually merge as well. That merger will also release gravitational waves and potentially gravitational recoil. Will that recoil be strong enough to eject the newly formed black hole from the center of Milkomeda? Probably not, given the relatively large ratio between their masses. However, studying extreme cases like Abell 2261 helps us better understand the physics of these processes and more accurately predict the distant future of our own galactic home. By understanding what can go wrong in the most massive systems, we gain a deeper comprehension of the rules governing our own galaxy's life and evolution. In a sense, by staring into the void of Abell 2261, we are peering into one of the most dramatic potential futures for our own corner of the universe. Let's pivot back to the James Webb Space Telescope and look at the specific observation programs designed to solve this puzzle. One key initiative is called PRIME, which stands for Primordial-like Resolved Investigations of a Missing Black Hole E. The goal of PRIME is to capture ultra-deep images of the cluster's central region using multiple infrared filters. This data will allow scientists to create incredibly detailed maps, charting the color and brightness of the stellar population. These maps, in turn, will help determine the age and chemical composition of stars across different regions of the galaxy. If the core was disrupted by gravitational recoil, we should observe a relatively uniform distribution of ancient stars. However, if the material was instead excavated by a binary black hole system, we would expect a much more complex structure, showing distinct populations of stars on different orbital paths. Another observation plan will utilize Webb's spectrograph to hunt for signs of accretion onto a potentially roaming black hole. Even if this object remains invisible in X-rays, the slightest amount of infalling gas should generate distinct emission lines in the infrared spectrum, lines that Webb is uniquely equipped to capture. A third critical element involves searching for those predicted hypercompact stellar clusters. Webb won't just photograph them, it will obtain their spectra. This spectral analysis is crucial to confirm that these clusters truly consist of stars ejected from the galactic center and are not simply random background objects. These observations demand dozens of hours of the telescope's incredibly precious time, and the subsequent data processing will span many months. Yet a major breakthrough most likely awaits us at the end of this long process. The scientific community is collectively holding its breath in anticipation of these results. This represents one of those rare instances where a single, focused set of observations could finally resolve a mystery that has baffled astronomers for years. But let's take a moment to consider the psychological aspect of this puzzle for the scientists themselves. Tackling a problem like this is a marathon, not a sprint. It requires years of meticulous effort, sleepless nights spent analyzing data, and constant self-doubt. Imagine a PhD student who dedicates several years of their life searching for a signal from a rogue black hole only to find nothing but noise. Or picture a theorist who constructs an elegant model only to have new, incoming data completely disprove it. This demands immense patience and, crucially, intellectual honesty. You have to be ready to discard your most cherished hypothesis if the facts contradict it. But that, ultimately, is the beauty of the scientific method. It is a continuous process of self-correction, a movement towards the truth through errors and refutations. The Abell 2061 mystery isn't just a competition between different ideas. It's a collaborative effort involving dozens, perhaps hundreds, of scientists globally. Observers using various telescopes share their raw data. Theorists and simulators compare their complex models against that data. This results in a constant dialogue, one that sometimes escalates into fierce debates at international conferences. But everyone shares the same single goal: to understand what truly happened out there. This collective passion for knowledge, this shared drive to solve a puzzle thrown at us by nature, is the central engine of science itself. And even if we don't find the definitive answer anytime soon, the process of the search will already enrich us with new knowledge, new methods, and even newer questions. Beyond the two primary hypotheses, ejection and core stripping, there are also hybrid scenarios. It's entirely possible that both mechanisms played a role. Imagine a situation where two galaxies merge. Their black holes form a binary system, which immediately starts scattering stars out of the core, making the galactic center diffused and fuzzy. After some time, these two black holes finally merge. At the moment of coalescence, a gravitational recoil, or kick, occurred. But because the core had already been disrupted and softened, even a relatively weak gravitational kick might have been enough to launch the newly formed black hole out of the galaxy. In this scenario, we are dealing with a combination of two mutually reinforcing effects. This would neatly explain why the system appears so extreme. First, a slow destruction of the core from the inside, and then the final powerful blow that ejected the central object completely. So, while these hybrid models are more complicated to analyze, they are likely more realistic. The universe is rarely simple or elegant. More often, multiple different processes are happening simultaneously. The main challenge lies in untangling this complex web and figuring out which process was actually dominant. Again, detailed observations are the only way to find the key to this puzzle. For instance, if Webb detects that the stellar halo exhibits a very specific asymmetrical morphology, it could be a direct indicator of this exact two-stage process. Searching for these subtle signatures, these cosmic scars left on the body of the galaxy by ancient cataclysms, is the primary goal of observational astronomy in this field. It's fascinating to compare Abell 2261 with other known troublesome or anomalous clusters. Is it completely unique, or are there other similar cases out there? Astronomers are actively searching for other examples of galaxies with missing cores, and a few strong candidates have already been identified. For instance, within the Virgo cluster, there's the galaxy NGC 4486b, which orbits the giant galaxy Messier 87. It also possesses a double nucleus, which could be the sign of a recent merger, and an unresolved binary black hole system. Another example is Abell 779. Right at its center, we also find a galaxy featuring a highly diffuse core. However, none of these cases are quite as extreme as Abell 2261. In those instances, the cores are either not as dim, or there are other indicators suggesting more standard astrophysical processes at work. For now, Abell 2261 remains the clear record holder, the most striking example of this anomaly. This effectively makes it the ideal laboratory for studying this phenomenon. By concentrating our most advanced instruments on this single object, we can hope to understand the physics of the process in its purest and most extreme manifestation. Then, armed with this key knowledge, we can circle back to the other, less pronounced cases and determine whether they are truly part of the same overall phenomenon. It is often true in science that studying one single, extremely unusual object can yield greater understanding than gathering statistics on hundreds of normal ones. Let's imagine for a moment that the James Webb Space Telescope actually found it, a small, compact cluster of stars far away from the galactic core. Its spectrum reveals stars moving at tremendous velocities, betraying the presence of an unseen, massive object at the cluster's center. This is it, the ejected supermassive black hole and its accompanying stellar entourage. What would be the reaction of the scientific community? It would be the top story in every major scientific journal and conference. It would be a triumph for Einstein's general theory of relativity, providing yet another stunning confirmation of its predictions. It would open a new chapter in the study of galactic evolution. Scientists worldwide would scramble to study this object, attempting to measure its mass, velocity, and trajectory. Theorists would compete to see whose merger model best explains the measured kick velocity. It would be a true eureka moment for an entire generation of astrophysicists. But what if the opposite happens? What if Webb's deepest observations reveal nothing at all? No wandering black hole, no dual nucleus, no obvious explanations? What if the galactic center turns out to be simply empty and quiescent? That would arguably be an even more exciting or profoundly perplexing result. It would mean that we fundamentally misunderstand something. It would point to a significant gap in our knowledge, demanding new physics. This wouldn't be the end of the story, it would be the true beginning. It would force an entire generation of young scientists to search for radical, unprecedented ideas. And it is precisely these moments of complete bewilderment in the face of nature, that drive science forward. Whatever the answer, we stand to win. We will either confirm our boldest theories or unlock the door to a completely unexplored realm of knowledge. As we wrap up this long journey, let's take one final look at the night sky. When we gaze at the stars, we immediately perceive order and harmony. Planets follow their fixed orbits, stars shine steadily for billions of years, and galaxies drift majestically through the cosmic void. But the story of Abell 2261 reminds us that beneath this surface of serenity lie processes of unimaginable power and chaos. The universe is not a static painting, it's a dynamic, ever-changing environment. It's a place where galaxies collide, black holes merge, and entire star systems can be hurled into the intergalactic darkness. This puzzle serves as a powerful reminder of how little we truly know. We've only just begun scratching the surface, exploring our cosmos with the help of our telescopes. Every new mystery, like this one, shows us just how much remains to be discovered. It fosters humility in the face of the universe's sheer scale and complexity. Yet, at the same time, it fills us with both hope and excitement. Hope that, using our intellect and our instruments, we might still solve these cosmic puzzles. And the thrill of pioneers standing on the threshold of a new, unexplored world. The mystery of the missing galaxy isn't just a scientific problem, it is an unfolding adventure taking place right before our eyes. And we, you and I, are its witnesses. Let us hope that the next chapter of this incredible story is revealed to us soon. So, we've reached the end of our journey into the heart of the Abell 2261 cluster. Let's recap what we've discovered. We've encountered one of the most intriguing puzzles in modern astronomy. The core, and potentially the supermassive black hole, is missing from the center of one of the universe's most massive galaxies. We have two primary theories, two main suspects. The first is the gravitational recoil scenario. A catastrophic merger of two black holes created such a powerful burst of gravitational waves that the newborn monster was shot out of its host galaxy like a cannonball, leaving behind a puffy and depleted stellar halo. The second is the core scouring scenario. The center hides not a single black hole, but a binary or even a triple system. This system's powerful gravitational dance, lasting billions of years, simply swept all the stars out of the central region. Both theories have their merits and drawbacks, and neither has received definitive confirmation yet. Observations using the world's best telescopes like Hubble and Chandra still haven't managed to find that smoking gun. All hope now rests on the James Webb Space Telescope. It might be staring into this cosmic mystery right now, and its data could radically change our understanding of galaxy evolution. This entire story is a vivid reminder that the universe is still full of surprises and that the most fundamental questions about its structure are still waiting for answers. Thank you for spending this time diving into this cosmic abyss with us. I hope this discussion leaves you feeling suitably impressed by the grandeur and mysteries of our universe, and that you sleep well. Make sure to subscribe to the channel so you don't miss future stories, and hit that like button if you found this fascinating. Now for the big question for you: which theory seems more plausible, the ejected black hole or the gravitational dance of multiple monsters? Or perhaps you have your own completely wild theory. Share your thoughts in the comments below. Good night,